But we are to use the definition of derivative to show that such is the case, right? Pictures aren't good enough. We need an analytic approach. So I need to show, I'm going to show it's not differentiable at 1. Get a little bit clearer. Part B is to use the definition of derivative to show not differentiable, i.e. no derivative, at that location where the two curves coalesce at x equals 1. So I need to show then, what does that mean? It's not differentiable at 1. And show that f prime at 1 does not exist. And in this case, judging by the picture, like I was saying earlier, it will be because the two one-sided limits of the derivative are not the same, right? You can kind of tell that in advance that that's your goal because of the way the picture looks, and it's a cusp. But there's a lot of ways the derivative cannot exist. We mentioned before, infinite slope and things like that. Anyway, so we need to show f prime 1 does not exist. So what is f prime 1? F prime 1, according to the definition of derivative, is this limit. So there's two ways to look at it. It's either as x approaches 1, f of x minus f of 1 over x minus 1, or I can use the other form, it really doesn't matter, h approaches 0, of f of 1 plus h minus f of 1 all over h. So those are my two options. I need to show either this limit does not exist or this limit does not exist. I can show that because these limits, right, specifically the limit of difference quotients here, they are the derivative, so therefore if the limit doesn't exist for this particular structure, then that means the derivative itself does not exist at 1. So I will just take the first one here. I'll use the x approaching 1 as opposed to h approaching 0, even though they are the same. So limit as x approaches 1 from the left. As x approaches 1 from the left, right, according to the picture or according to the rule, either one, as I approach 1 from the left, I'm on the 2 root x curve. Right? So I will replace the function symbol here, f of x, for this particular function, this piecewise function, with the appropriate rule, which is 2 root x in this case. So I have 2 root x minus 2 root 1. I'm just filling in f of x and f of 1 for the correct piece of the function. And x minus 1 down here stays the same. Okay, so we see we can take out a 2. And when we do that, we will end up with root x minus 1, I guess 1, I don't need root 1 anymore, and x minus 1 down here. And as we run the limit, I should probably use the conjugate, because again, it's a 0, 0 case for all these derivatives. I got to find some manipulation algebraically or otherwise to conclude what the value here is and get rid of this x minus 1 on the bottom is the real issue. So using the conjugate, as we've seen before, you have root x plus 1 over root x plus 1 here. So simplifying a little bit, now I have the limit as x approaches 1 from the left of 2. Root x minus 1, root x plus 1, of course, becomes x minus 1. So we have x minus 1 over x minus 1. Those are going to cancel. That was our algebraic trick here to take care of the bottom going to 0 is no longer happening. And we have root x plus 1 still down here. That's fine. And now as x approaches 1 from the left, root of x, right? This function here, of course, just approaches the root of 1, right? From the left, but it doesn't really matter. It approaches root of 1. So we have 2 over 2, which is 1. So it looks like it's approaching a slope of 1. So let's go back to the picture very quickly, and we see that the red line, red tangent line I was talking about, right, as we moved up the curve here, right, as it actually approaches 1, we move up the curve with the tangent lines. The tangent line slope here was approaching, looks like, a value of 1. And in my picture, it's not that bad. The picture is fairly accurate if you look here. Right? There's the delta y and delta x. So y, delta x. It is 1 unit by 1 unit. It is a slope of 1, just like we got down here. The picture is halfway accurate.